First is point estimation. Point estimation is the process of finding an approximate value of some parameter. Okay, like parameter denote the theta. Okay, then the point estimator is statistic, is to estimate point. Okay, so is expressed as theta hat. The point estimate means the obtained value from the sample. Okay, the value. Okay, so let's look at a BMI example. If the parameter is considered mu, that means the average BMI of the population in the sample of 100 people, the point estimator mu hat is the sample mean x bar. Okay, so like this, equal the function of sample. When you have the sample data, you can have the point estimate mu hat equal 32 kilogram per square meter. Okay, I have a question here. Why do we use the sample mean as an estimator of mu? As your central location measure, you also learn median or mode, right? Couldn't we use median or mode as an estimator of mu, like this? Or so we need to look at good estimator condition. Okay, and there are 3 conditions for a good estimator. As you know, the estimator always has a sample error. Okay, the sample error is defined as theta hat minus theta. Okay, or like this. Okay, and it can be expressed as like this. Go theta hat minus the expected value of theta hat plus expected value of theta hat minus theta. Okay. The theta hat minus the expected value of theta hat means deviation. Okay, of theta hat. It is the variance part. Okay, and the expectation minus theta means the bias. Okay, therefore sample error can be divided into variance part and bias part, and the smallest of these 2 parts can be considered a good estimator. Okay, like this. Using this concept, the 3 conditions for good estimator are unbiasedness and efficiency and consistency. Okay, unbiasedness means the expected value of estimator equal parameter. The bias means the difference value between expected value of theta and theta. Okay, then unbiasedness means the bias equal 0. That is the expected value of theta hat equal theta. Efficiency is the estimator has the smallest variance of all estimator which could be used. That is, assume that there are two estimator, theta hat 1 and theta hat 2. And then the variance of theta hat 1 less than the variance of theta hat 2, and we can say that theta 1 is more efficient than theta 2. Okay. Constancy is the value of the estimator approach. The value of parameter at the sample size increase, so like this. Okay. So let's take a look at these three conditions in detail. Unbiasedness is that expected value of estimator equal parameter. So if the expected value of an estimator is theta, that is when the bias equals 0, then the estimator is called an unbiased estimator of theta. Okay, for short, UE of theta. Conversely, though the expected value is not equal theta, then the theta is colder on biased estimator with the bias side equal like this. Okay. Let's look at this graph. Here are distribution of two estimates. The red and blue. Okay. Red is the distribution of theta hat 1, and the blue is the distribution of theta 2, and theta is here. Okay. At this time, the expected value of theta hat 1 equal the theta. Okay, that is the bias equal 0. Therefore, theta 1 is an unbiased estimator of theta. Okay. On the other hand, since the expected value of theta hat 2 here, the bias is about this. Okay. This the distance equal bias of theta hat 2. Okay, so theta hat 2 is a bias estimator. Okay. So the theta hat 1 is a good estimator. Then there is theta 2. Okay. In their bias aspect. Okay. let's look at an example. We consider the estimator of mu is the x bar, the sample mean, that is theta mu or theta hat, like this. Okay. Then the x bar is an unbiased estimator of mu. Okay. This can be easily provided as follow. The expected value of x bar equal, so like this, x1 plus x2 and by small n and equal, small n, it means the sample size is we can consider constant, so this. Okay, so instead using the property of expectation, we can write this. And we assume that the IT independent identically distribution, so equal mu, so multiply and mu, so we can cancel out, equal mu, that is like this. Okay, Mr. Sarah. And next, the unbiased estimator for sigma square, that is population variance, is the sample variance. Okay, a large S square, like this. You learn that the sample variance is divided by the n minus 1. It is not n. Okay, this is because the sample variance is an unbiased estimator of the population variance square, that is like this. Okay, so now I will try to prove this in detail. Okay, so the expected value of the sample variance equal like this. Okay, it is the constant, so like this. Okay, and then I'll replace the expected value with the alphabet large A. So the large A equal like this. you know, the this term is not depend the small I. Okay, so it is the small the x bar square plus x bar square plus n times. Okay, so equal n multiply x bar square, and you know it means since the sample mean is called x bar, so the summation of xi equal n multiply x bar. Okay, so square it means the minus 2 and x bar square. Okay, so it means equal minus and multiply x bar square, so it equal okay it is equal the expected value of sigma I equals n xi square minus x bar square. There it is the constant, so it can the out, so we can write the n multiply expecting of x bar square, and you know the expected value of x equal mu, and the expected value of x square minus the expected value of x square equal the population variance. So the expected value of x square means the sigma square plus the mu square. Okay, okay, so like this. So this term is like this: x1 square plus x2 square plus xn square equal here. You know the x follow. We assume that the x follow I D. It means the mu plus sigma square. It means the mu plus sigma square. So equal n multiply mu plus sigma square. And the second term, you know, it is n. Okay. you know, the variance of x bar equal, you know, the sigma square divide the small n. You know, it means the expected value of x bar square minus the expected value of x bar square. Okay, you know, it means the mu square. So the expected value of x bar square equal sigma square over n plus mu square. Just like this. Okay. To sum up, you know, the first term is okay, like this. And multiply mu plus sigma square minus n multiply like this. And sigma square plus mu square. So equal minus like this square minus n mu square. So it is a cancel out equal and sigma square minus square minus sigma square. Therefore, large A equal n minus 1 multiply sigma square. So 1 multiply square to cancel out equal sigma square. So the reason for dividing by n minus 1 when obtain a sample variance is that it satisfies the unbiased estimator. Okay. There are 3 estimators for estimating the population mean mu, like this: x bar plus 1 over 1000, and x bar plus 1 over the sample size n. Okay, they check the unbiasedness of the following estimators. You know, the x bar is unbiased estimator of mu. That is like this, mu. Okay, and the second estimator, x bar plus 1 over 1000 and equal plus is a constant, so 1. It is a mu, so mu plus 10,000. Okay, so it is not equal mu. Okay, so the estimator is the biased estimator. Okay, and with the bias side equal 1 over 1000. And third, the estimator called x bar plus 1 over sample size small n. The big value x bar plus n equal n equal mu plus 1 over n. So it is not equal mu. Okay, but as a sample size increase go to infinite, and the bias size goes to 0. Okay, so the estimator become the unbiased estimator. Okay, so the third estimator it depends on the sample size small n. Okay, the second is efficiency. It is also called relative efficiency. As you know, the estimator had their distribution like this, and estimator has the variance. Okay, it is called the error, and the standard deviation of theta hat is the standard error, like this. And if the variance among the estimates is the smallest, the estimate is considered to have relative efficiency. Okay, let's look at the distribution of the following two estimates. Okay, as you can see in the figure, the variance of theta hat 1 is smaller than of theta 2. Okay, so like this. Therefore, theta 1 has more efficiency than theta 2. Okay. So if the theta hat 1 and theta 2 are unbiased estimator, have both unbiased estimator, then since the variance of theta 1 hat less than the variance of theta hat 2, so theta 1 is a good estimator than theta 2. Okay, let's look at example. There are three estimators like this. So compare the efficiency of the following estimators. The variance of x bar equal sigma square divide the small n. And second estimator, like this, by the property of variance, let's say equal x bar. Okay, because the constant does not affect the result of variance. Okay, so equal the sigma square over n. Also, the third estimator, plus and equal, it is also we can consider a constant, so the variance x bar equal n. So the variance of these three estimator are all the same. Okay, the third condition for good estimator is constancy. Okay, constancy is that the value of estimator approach the value of parameter as the sample size increase. Okay, in the convergence in probability concept, that is the probability of between theta hat and theta less than some constant, the epsilon, goes to 1 as sample size increase, or the probability the theta hat minus the absolute value greater than epsilon goes to 0. The sample size goes to infinite. Okay. Then the zeta hat is called the constant estimator, and we can write it like this. Okay. Those variance of the sample mean, that x bar is sigma square divided by the sample size small n. So as the sample size goes to infinite, then the variance of the sample mean goes to 0. Okay, so the x bar convergence in probability to mu. Okay. So x bar is the consistent estimator of mu. Okay. If mu hat, the estimator of mu is that as follow. That is the summation of xi over n minus 1. Okay, and then the it is a constant estimator of mu. Okay, and the sample size increase, and there bar mu equal 1, no, n minus 1 square I equal it means the n sigma square. So n minus 1 square and sigma square. Okay, then as the sample size increase, then the variance of the estimator goes to 0. So the mu hat convergence in probability mu. Okay, so it also mu hat is a constant estimator of mu. It's like to check the constancy of the following this estimator. The x bar convergence probability mu. So x bar is the consistent estimator, and second estimator zeta hat 2 x bar plus 1 over 1000 goes the convergence probability. The x bar goes to mu, and 1 over 1000 is constant. So mu plus 1 over 1000. It is not mu. So the zeta hat 2 is not constant estimator. And third estimate estimator that has 3 equal plus n conversion probability equal mu 1 over n as the sample size goes infinite, this term goes to 0, so equal mu. So the set has 3 is also consistent estimator. Okay. So to sum up, for unbiasedness, the estimator X bar is unbiased estimator, and X bar plus 1 over 1000 is not the unbiased estimator. That is, the bias is 1 over 1000. And the third, the estimator has the bias, the 1 over the sample size n. However, as the sample size increase, then the bias goes to 0. So we let the triangle. Okay. In efficiency, since all 3 estimator have the equal variance like this. Okay, so no one estimator has better efficiency. Okay, as you know, the X bar is constant estimator. Okay, and the second estimator is not satisfied the constancy. Okay, and the third estimator constant estimator, because the 1 over n converts to 0 when the sample size goes infinite. So in summary, the X bar has a good condition as an estimator of mu, and when the sample size increase, the third estimator, that is X bar plus 1 over n, can also good estimator. Therefore, through these conditions of good estimator, that unbiasedness and efficiency and the constancy. So when the parameter mu, sigma square, sigma the population proportion, then we use the sample mean, sample variance, sample standard deviation, sample proportion respectively. Okay.